Hello viewers, welcome you all. So in this lecture, I am going to start the next unit of solid state physics, and the unit is lattice vibrations. Lattice vibrations, right? So this unit again is an important unit, right, in solid state physics, and question can be asked from this unit in competitive exams. So if I divide this entire unit in three important sections, right, then I have three sections. The first one is phonons. Phonons, right? I mean the properties, interactions of the phonon, concept of phonon, right? The second one is lattice vibrations in one-dimensional monoatomic lattice. Lattice dynamics of one-dimensional monatomic lattice, then diatomic lattice, right? This is the second part, and the third part is that is very important, theories of specific heat of solids. So in this chapter, this one, specific heat theories. We have three specific heat theories. I will discuss it in this lecture. This is the most important one, right? And usually question is asked from here. But these are the three topics from where the question can be asked, right? Phonons, concept of phonons, monatomic lattice dynamics, diatomic lattice dynamics, and theory of specific heat of the solids, right? So I will cover these three important topics, important points, in fact, of these three important topics of this unit. So I am starting with the concept of phonons. Concept of phonons, or concept of a phonon. So to understand the concept of phonon, we have to look at the crystal lattice. We know very well, I have told you in the earlier lecture, that crystal lattice is basically a collection of points in the space in such a way that the environment about each point is same in the entire space lattice or crystal lattice. And when we place atom or a group of atom in that lattice, it lead to the formation of crystal structure. Now I can say, if I consider a two-dimensional crystal structure, like this is the two-dimensional crystal structure. This is the atom, this is the atom, this is the atom, this is the atom, this one, this one, this one, this one, and then this one, this one, this one. All these are the atoms inside the crystal structure, atoms or group of atoms. Now we can see that these atoms are bonded together by means of electrostatic forces. Either there is covalent bond, metallic bond, ionic bond, or van der Waals bond, right? So they are bonded together with each other. So we can say that these are connected through the elastic strings, right? I am representing here elastic string. Why they are elastic string? I will explain you why we are calling them as elastic strings or springs. You can see here, all the individual atoms are connected with each other. Now, why I am saying that these atoms are connected by elastic springs or strings? Because we know very well, when pressure is applied on the solid or the temperature of the solid is increased, the individual atoms that are placed at the different positions, now they will try to change their position. If the temperature is increased, their thermal vibrations will increase. Now when their vibration increase, they try to leave their original position. but this is not allowed if they want to go toward this side, because they are pulled by this atom, right, back toward this side by means of electrostatic force of attraction. Similarly, if it want to go toward this side, it is attracted. So we can say these electrostatic forces are acting like a spring, right? So they are taking the atom back to its original position. So we can say the individual atoms, they are behaving like harmonic oscillators. They are oscillating about their equilibrium position, right? So now we also see here that when one atom is disturbed, suppose this atom is disturbed, then it is not like that this only this atom will remain disturbed. This disturbance will be traveled to the entire lattice through these elastic springs, and all the atoms, these atoms, they will start oscillating, right? So this entire dynamics, oscillations of the crystal is known as lattice vibrations, right? And these lattice vibration can occur because of internal dynamics, right, and external dynamics. Both the cases are there, right? Internally they can be excited, but they can be excited by means of external things like applying pressure, raising the temperature, using electromagnetic radiations for excitation. So in this way, we can say that the lattice vibration can be created inside the crystal lattice. Now, we know very well from the quantum theory of harmonic oscillator that the energy of a harmonic oscillator in quantum mechanics is n plus 1 by 2 h nu, right? So when one atom, because it is behaving like a harmonic oscillator, it means its energy is quantized. It can have energy in the lowest energy state, E0 is equal to 1 by 2 h nu, then E1 is equal to 3 by 2 h nu, then E2 5 by 2 h nu. So it can go from one energy state to another state, right, by acquiring energy, or it can come back to the lower energy state by radiating some energy. So that energy which is either absorbed or evolved during these lattice vibrations, that quantum of energy is called phonon, right? This word has been chosen in analog with word photon, that is the quantum of energy in electromagnetic radiations, right? So this is phonon. The quantum of energy in lattice vibrations is known as a phonon, right? And it has almost similar properties as that of a photon. We know very well photon is a boson. So phonon is also a boson, means it has a integral spin and its spin is 0, right? It obeys Einstein statistics, right? Now we know very well that a photon travels with the speed of light, c, but a phonon travel with the velocity of sound, right? That is approximately 332 meter per second. This is the velocity of a phonon, right? We know a photon has some momentum. P is equal to h nu upon c. This is the momentum of photon. But phonon, it does not carry, it does not have any momentum, but it behaves in such a way while interacting with the crystal atoms that it is carrying a momentum h cut k, right? This is the momentum that is supposed to be possessed by phonon, although it is not carrying any momentum, but it is behaving like a particle that has momentum, this, and this is usually the momentum of a crystal structure, right? So here h cut, we know very well what it is. K is the wave vector of phonon, right? So these are some properties of phonons, right? Now the phonon inside the given crystal lattice can be acoustical and they can be optical, right? Acoustical means they are associated with acoustics, right? Sound waves, thermal energy. Optical means they are associated with the electromagnetic wave. They are excited because of the electromagnetic wave interaction with the crystal lattice. So they can be of two type, optical and acoustical, right? So we have to remember all these properties of phonon. Now I am going to the inelastic scattering of inelastic scattering of phonon by a photon. This is also an important one, right? So suppose we have a phonon that is photon that is coming here, and it is interacting with the photon. Right, this is photon that has a wave vector small k, right? And here we have a phonon, right? Then when it is scattered by this photon, when this photon is scattered by this phonon, then it travel in this direction, right? This is now wave vector small k dash, right? It is incident and it is scattered. And we also have a phonon that is produced here, that is recoiled through this direction, and this is the incident direction. So this angle phi is the angle of scattering of a photon, right? This is photon and this is a phonon. Phonon has wave vector capital K vector, okay? And this is small k, this is small k, right? So now this was the inelastic scattering of a phonon by photon, right? Or you can say photon by phonon. So there is an interaction between these two particles. This is a photon coming in this direction. This is a phonon. When they undergo collision, we have this kind of interaction, and then we have a formula for that is given as omega is equal to 2 bs omega n divided by c into sine of phi by 2, right? This is the angular frequency. Omega is the angular frequency of a phonon, right? Omega is equal to 2. Vs is the speed of sound in the crystal, right? Speed of sound in the crystal. Vega is the angular frequency of photon, right? And n is the refractive index of the crystal. C is the velocity of light, phi is the angle of scattering, right? So this is the equation that is for the angular frequency of phonon that is produced during the interaction of a photon of light with a phonon, right? So we have to remember this relation. Omega is equal to 2 bs omega n divided by c into sine of phi by 2. So these are some facts related to the phonon which can be asked in any exam. Now I am going to the second part of this unit, that is lattice vibrations of a one-dimensional monoatomic lattice, right? Lattice vibrations of a one-dimensional monoatomic lattice. So here, one-dimensional monoatomic lattice means we are considering only one-dimensional case, right? And monoatomic means the atom in the crystal lattice are all are same. Mono means the basis that is of a single atom, right? We can say like copper, right? or it can be anything else. But if I take the case of sodium chloride, then we have a diatomic, right? Two different atoms are there. So monoatomic means all the space lattice is made up of a single type of atom. So we are considering only one dimensional case, right? Or we can say all these atoms are connected by means of elastic strings, right? So when we apply pressure on these springs, they will start vibrating. Vibrations will be produced in this string, and the individual atoms will get displaced from their equilibrium position. That small m is the mass of individual atom, capital S is the force constant, or we can say string constant, right? And when we simplify this problem, then we derive a relation for dispersion relation, that is vega is equal to under root of 4s upon m magnitude of sine of capital K A upon 2. Here A is this is equilibrium separation between the two atoms, that is lattice constant. We called it as lattice constant A, right? We know very well. It is the equilibrium means when no vibrations were there. So the minimum distance between the two atoms is a lattice constant, right? Here vega, this vega is the angular frequency of the vibrations that are produced inside the crystal lattice, right? Now this relation is called a dispersion relation, right? It can be further studied, right? We can check that what is the condition for dispersion to take place. We know very well dispersion takes place when phase velocity is not equal to group velocity, and the other thing is that the velocity of the wave in a medium is dependent on its wavelength. We can say like that. So when velocity of the wave, whether it is phase velocity or group velocity, if it depend upon the wavelength, right, then that medium is a dispersive medium, right? So by using this dispersion relation, I can check that when the dispersion will take place. So we have two conditions for monatomic lattice. The first one is the condition when we have small frequencies of vibrations, right? So when frequencies are small, right, we know very well K is equal to 2 pi upon lambda, wave vector for phonon, wavelength is very large, right? So in that case, when K is small, theta tends to 0, so sine theta tends to theta, right? So in that case, sine Ka by 2, I can write it as Ka by 2. I can calculate the phase velocity and group velocity. So in that case, B phase velocity will be S upon M under root into A, and V group velocity again same S upon M under root A. So you see here that both these velocities are equal and they are independent of the wavelength. Wavelength means K. It is not appearing anywhere. So we can say that in this case, when the frequencies of the vibrations are very, very small, in that case, we will not have any dispersion. The medium is behaving like a non-dispersive medium. The crystal is behaving like a non-dispersive. But the second condition, when frequency is high. So when the frequency is high, in that case, I can't take this. It means wavelength is small. So in that case, I can't take theta tends to 0. So in that case, I'm not going into all. We can say we can see from here that when this theta is not equal to 0, I can't write sine theta is equal to theta. So in that case, when I will simplify it and calculate the phase velocity and group velocity, I will find that group velocity and phase velocity, they are not equal, the one thing, and also they are dependent on K. They are dependent on K, right? I'm not writing the expression, but we have to remember they are dependent on K. It means in this particular case, we will get dispersion. Or we can say now for higher frequencies, the medium is behaving like a dispersive medium. So this is the condition that we have always remember, that for a monatomic lattice, right, one dimensional monatomic lattice, when the dispersion take place, so it take place for the high frequencies of the lattice vibrations, but no dispersion take place when this is frequency is small, you can see here, right. So this was the first case. Now I am going to the second case, that is lattice vibrations of a one dimensional diatomic lattice. Diatomic means, in this case, the entire crystal structure is made up of two type of atoms, right? One is having mass m1 and other is having mass m2, right? So these two type of atoms are connected with each other by means of elastic strings, we can say. So we can consider one dimensional array in the same way, like this is the first atom, this is this atom, this one, then this one, these three atoms are there, and we have a second atom, and a second atom. So as I told you that we have two type of atoms. First one is mass m1, second is m2, m1, m2, m1, m2, m1, and they are connected by means of elastic strings with each other. So again, we are doing the same thing. We are considering the vibrations of this array of atoms. What we are considering only one dimensional case. So again, what we will do, we will find a relation, right? So in this case, when we simplify it and we found the dispersion relation, then it comes out to be vega square is equal to S into 1 upon m1 plus 1 upon m2, right, plus minus S under root of 1 upon m1 plus 1 upon m2 whole square minus 4 sine square Ka divided by m1 m2. So you can see here that in this case the dispersion relation is quite complicated, and it is although also difficult to remember this entire relation, right? So now we have to only remember what are the results that come out of this relation. There is no need to go for memorizing all these equations, but what are the results that come from this relation, right, as we have discussed for the monatomic lattice, right? We can see from this relation that we have now positive and negative sign here. It means two value of vega square are positive. One corresponds to vega positive and one corresponds to vega negative when we will simplify it, right? I mean, I can write two equation out of this, like this, it is equation number one corresponding to equation number one corresponding to positive sign and other corresponding to negative sign. After solving, for the positive sign we will get vega positive, and for the negative sign we will get vega negative. So the two values of the frequencies are possible for diatomic lattice. If I plot a graph between vega and k, right, then I get two graphs, right, one with vega positive and k, right, and other vega negative and k. This graph is known as a optical branch, right, and this is known as acoustical. Because vega negative means we are dealing with the lower frequency, vega positive means we are dealing with the higher frequencies. So higher frequency is optical, lower frequency is acoustical branch, right? One thing that I can also discuss from this relation one, that is, if I apply the condition again for longer wavelengths, right, means in that case Ka, right, you can see here Ka, it is very greater than very less than 1, because K is equal to 2 pi upon lambda. I was saying for the longer wavelengths, right? small frequencies. So if I simplify this equation, again I will get two values. One corresponds to vega positive and one corresponds to vega negative. When we simplify it, we get 2s upon m1, and here we will get 2s upon m2. So these are the two values. Now you can see if both the atoms are same, their mass will be same. We will get vega positive is equal to vega negative, and that is equal to 2s upon m, right? So these are some important points that we have to remember for the case of a diatomic lattice. This relation, right? Two branches in the WK graph, right? And then condition for a longer wavelengths or small frequencies, right? So this was the second topic of the lattice vibration of one dimensional and monatomic and diatomic lattice. Now I am coming to the third topic, that is specific heat of solids. Now we know very well, first of all, we have to know that what is specific heat, right? We know very well specific heat is defined as the amount of heat energy required to raise the temperature of a unit gram of substance through unit degree, right? We can say 1 gram of substance through 1 degree. We call that as a specific heat of solids, right? Or we can say that it is defined as the amount of heat required to raise the temperature of unit mass of the substance through unit Kelvin. We can also say in that way, right? Usually the specific heat of the solid is expressed at constant volume, right? So we call it as a CB, right? Although we know what is the relation between Cp and Cv, we also have Cp, constant pressure, but for solids we mostly consider Cv. I'm not going into Cp or Cv because they are all specific heats, but the thing is specific heat of solids, right? Now we have three different theories, right? The first one is a classical theory. That was given by Dulong and Petit's, and it was known as Dulong-Petit's law, right? And according to this theory, the specific heat of the solid is always constant, right? Dulong and Petit's law, right? According to this, specific heat of the solid is always constant, and it is equal to 3R. R is gas constant. It is around 6 calorie per mole. So if I plot a graph between temperature and specific heat, temperature, and this is specific heat. So as I told you that if I plot a graph between these two, then I found that this one. So according to Dulong and Petit's law, as I told you, it was given by Dulong and Petit's. They said that the specific heat of the solid is always constant and it is equal to this. But when we did the experimental observations, we plot a graph between the specific heat of the solids with temperature. We found that this law, Dulong and Petit's law, it is valid only at the higher temperatures, right? You can see when the temperature is high. But when the temperature is low, specific heat of the solids, decrease and it approaches to zero, right? With the decrease in temperature, and at very, very low temperature, it nearly becomes equal to zero. So it means the classical theory of the specific heat of the solids is wrong. It is valid only high temperatures, and according to it, the specific heat of the solids is this, right? Cv is equal to, I'm not going into the derivation, I'm writing it directly. So sometimes examiner ask you that what is the specific heat of the solid according to the classical theory or Dulong and Petit's law. So we have to remember that this is the case, right? Now To remove this discrepancy or to solve this puzzle, a theory was given by Albert Einstein. We call it as a Einstein theory of specific heat of solids. So the main crux or main point in the Einstein theory was that Einstein said that the atom inside the solid may be considered as independent harmonic oscillators, but all are identical, because we have seen in the case of lattice vibrations, right, they are behaving like a harmonic oscillator, right. So according to the Albert Einstein, right, all the atoms inside the crystal lattice or solid, they are behaving like a independent oscillators. So if they are behaving like independent oscillator, it means they can emit and absorb energy as per the rules of a harmonic oscillator. So, right. But the main thing here in that we have to remember that in Einstein theory, all the atoms were independent oscillator. They were not coupled with each other. He considered that all are behaving like independent, right? And they are not having any kind of relation with the other oscillator, right? And they absorb and emit energy in discrete forms, right? So when we find the expression for the specific heat of the solids by using this Einstein theory, then that relation was, I am writing that relation directly according to this theory, that was CV specific heat is equal to 3R into theta E upon T whole square e raised to power theta E divided by T divided by e raised to power theta E divided by T minus 1 whole square. So this was the Einstein's result, right? Here R is gas constant. Theta E is called Einstein temperature and it is equal to H nu upon K, right? T is the temperature of the given material, right? We have to remember that this theta is equal to H nu upon Kb, Boltzmann constant. It is called Einstein temperature. So we have to remember this relation. It is very, very important, right? This is the relation for the specific heat of the solids according to the Einstein theory, right? Now, again, if we apply condition on this equation number 2, that first condition is a high temperature. Let's see what happened to this relation when the temperature is high. So when the temperature is high, if we solve it, then we found that Cv is equal to 3R. So it means it is in full agreement with the experimentally observing facts that very high temperature, specific heat of the solids is constant and it is equal to 3R, and it was Dulong and Patet's law. So the same thing, and obviously it is true, but what happened at low temperature? We are interested in that. So case number 2, low temperature. So when we apply the condition of low temperature here in equation number 2, then we found that at very, very low temperature, Cv, specific heat of the solid, that is equal to 3R into theta E upon T whole square e raised to power minus theta E upon T. So we got this relation. So we can say that the specific heat of the solid has two dependencies. When the temperature is very, very low, right, very, very low, then we can say that it is dependent on two factors, this one and this one, but we know exponential factor is dominating, so we can say Cv is directly proportional to e raised to power minus theta E upon T, right. So this is the result of Einstein. So obviously when the temperature will decrease, then if temperature approaches to 0, right, then what will be the case? E raised to power minus theta E upon 0 means minus infinity. E raised to power minus infinity tends to 0. So Cv tends to 0 as the temperature tends to 0, right? So sorry, this is the case, right? So, but again, when we did the experimental observations, we found that at very low temperature, right, the decrease in the specific heat of the solid, as per the Einstein theory, it was not in agreement with the experimental results, right? So it means there is some flaw in this theory also. So that flaw was later on addressed by the dy theory of specific heat of solids, right? Dy. Right? So whatever flaw was there, although this theory was sufficient to explain that at very low temperature, the specific heat decreases with decreasing temperature and it approaches zero at the temperature approaches to zero. But again, I'm saying that at very low temperature, the graphs that we obtained, they were not matching with the experimentally observed facts. So the discrepancy was removed by Lenzman dy, right? So the main point or main crux of dy theory that make it different from the Einstein theory was that it is considering atom inside the solid as a coupled oscillators rather than assuming them as an independent oscillator. I told you that in case of Einstein theory, atoms were taken as independent oscillators, but that was wrong. We know very well that atoms are attached with each other through electrostatic forces. So they should be treated as a coupled oscillator. So this was the difference, main difference between the dy theory and Einstein theory, right? So when Lenzman dy calculated the total vibrational energy of a given solid, then it comes out to be U is equal to 9n into T upon theta d power 3 k b t integration 0 to theta d upon t into x cube upon e raised to power x minus 1 dx. This is the expression for the total vibrational energy of the entire crystal. Now this expression is used for calculating the specific heat both at low temperature and at a high temperature. In this expression, we can see that theta d, again here theta d is equal to h nu d upon k b, right? Kb. Again, it is called dy temperature. Theta d is called dy temperature, and nu d is dy frequency, right? Kv is Boltzmann constant, T is temperature, x x is equal to, I am writing x is equal to, you can see here, h nu upon k b t, right? It is h, right? Sorry, x taken here. So you can see here that when we apply conditions on this expression, the first condition is when the temperature T is very high. T is very high. So at very high temperature, when we apply the condition of high temperature in this relation, that is equation number like 3, right? Earlier I have taken equation, yes. Then we found that at that temperature very high, Cv is equal to 3R. Again the same thing, right? It is constant. 3R means 6 calorie per. So the same thing that we got, that is Dulong and Petit's law. But when the temperature is very small, T is very small. When we applied this condition, then we got Cv directly proportional to T cube. So this is what we call as a dy T cube law, that at very low temperature, the specific heat of the solids is directly proportional to the cube of temperature, right? So this is d by t cube law. So we have to remember that this is d by t cube law and this is a Einstein theory, right, at low temperature. But at high temperature, all the three theories, classical theory, Einstein theory and dy theory, all gave the same result, that Cv is equal to 3R. That is Dulong and Petit's law, right? I think here n, I don't told you, n is the number of atoms in the crystal, right? And we have to remember that what is dy temperature, right? This is dy temperature, this is Einstein temperature. We have to remember expression for that. So this is all about the dy theory. Although dy theory do have some limitations, particularly when it is applied to the metals, right? It break down there. So I will explain you what happened to this dy t cube law when it is applied to the case of specific heat of metals. At that case, it got modified. So I will tell you about the modified form of dy t cube law for the metals. But for solids, right, general solids, Cv at very at low temperature is directly proportional to T cube, and at high temperature it is equal to 3R, right? So this is all about this chapter, this topic, these topics of this chapter, three topics: phonons, lattice vibrations of monatomic, diatomic, and three important theories. Once again I am saying three important theories of specific heat of the solids: classical theory, that is Dulong and Petit's law; Einstein theory, and then dy theory. The difference between Einstein and dy, right? And the results for the classical, Einstein and dy at high temperature and at very low temperature, right? So this is all about it. So thank you very much.